All right, so today we are going to be going over one of the most powerful tools that we have in science, and that is the periodic table. It can predict chemical reactions and it even organizes our building blocks of matter. It does so much more than what it seems to do. So, to begin, the periodic table organizes all of our known chemical elements by their properties. It organizes our known chemical elements in a way that is going to allow us to understand how they are going to function. And just by looking at that table, we can predict how our elements will behave in reactions, the kinds of bonds that they will form with other elements, and even the kinds of compounds that they might form. It's like the periodic table, it's like a map of the building blocks of matter. And the periodic table, it was actually developed in 1869 by Dmitry Mendeleev, and he organized these elements by their atomic mass, and then he grouped them by similar properties. And this organization that he did, it helped predict those properties of our undiscovered elements. But over time, this table, it has been updated as our understanding of atomic structures has grown. And today, instead of organizing the periodic table by their atomic mass, we organize it by the atomic number. So the periodic table is not just a chart. It is an extremely powerful tool that is going to help us understand and predict the behavior of matter. So to start, we're going to go over the layout of the periodic table. So the periodic table is divided into rows and columns. We call our rows periods and we call our columns groups. So the horizontal rows of the periodic table, those are called periods, and they are going to indicate the number of electron shells that we have in an atom. So for example, if we're going to look in period 3, we see that all of those elements, they're going to have 3 electron shells. Another example is if we look at calcium. Calcium is actually going to have 4 electron shells. And when we're taking a look at the vertical organization of the periodic table, they're referred to as groups. So these are our groups. And these are our periods. So the vertical columns of a period, they're going to show the elements that have chemical properties that are similar to each other. And they're similar because these groups, they're going to have the same number of valence electrons. And I need you guys to remember that valence, it refers to the outermost shell or electrons. And the valency of an atom is going to determine its bonding patterns. So when we're looking at group 2, like if we're looking at calcium, calcium is going to have only 2 valence electrons. If we're looking at carbon, carbon is in group 4, and that's going to have 4 valence electrons. When we are talking about our groups, it goes like this: 1, 2, 3, 4, 5, 6, 7, and 8. We're actually going to skip all of these transition metals as they have different properties. So understanding the number of valence electrons and the number of shells that an atom has is going to allow us to predict its chemical behavior, and it's going to allow us to understand its reactivity and how it bonds. So each box on the periodic table is going to give us information that is really important about that element. So within the box, we have the element symbol, and in this case, we're looking at carbon, which is symbolized by the letter C. And our element symbol, it can be either 1 or 2 letter abbreviations. So for example, we have K, which is potassium. We have Mg, which is magnesium, and so on. We are not normally going to see the element say its entire name like this. We are expected to know our abbreviations and their names, not of every single element, but at least the ones most important to us. So the next thing that we see in these boxes is the atomic number, which is 6 for carbon. The atomic number is going to tell us the amount of protons that we have in the nucleus. And that is really, really important because our protons, they define the element. So if we ever see an atom or an element that has 6 protons, it will only ever be carbon. Even if we look at this table right here, if we look at lithium and we see the number 3 protons will always be lithium. It will never ever be anything else. The number of protons is going to define the element that we are talking about. And the next thing that we see in the boxes is the atomic mass. The atomic mass for carbon is 12. And our atomic mass, it actually is described in the units of Daltons or AMU, right? Okay, so atomic mass units. Dalton or AMU, which is atomic mass unit. And they have a relationship which is 1 to 1. So 1 Dalton is equal to 1 AMU. We can use that interchangeably. And the average weight of our atom, that is what our atomic mass is telling us, and it is the weight of our protons and our neutrons. So every single proton has the weight of 1 Dalton, and every single neutron has the weight of 1 Dalton. We do not consider our electrons when we're talking about the atomic mass because they are so lightweight that they are negligible to the weight of that atom. So the elements, they are categorized by a few different ways, and the way that they are categorized is going to depend on their characteristics. So first, we have our metals. And our metals, they are very good conductors of heat and electricity. They're very malleable, so they're movable, and they have a shiny appearance. Examples of our metals, it includes iron and gold. Our metals, they are very important to us in the world of construction, in the world of transportation, because of how strong they are, how durable they are, and their conductivity as well. And up next, we have our non-metals. Our non-metals are very poor conductors. They are really brittle and they're actually very dull in appearance. So non-metals include oxygen, it includes sulfur also, and these elements, our non-metals, they are super essential for life processes like respiration. They play really big roles in industries, and they're just very important to life processes. So the next category that we have are our metalloids. Our metalloids, they are like hybrids of metals and non-metals. They have properties of both metals and non-metals. An example of a metalloid would be silicone. And silicone is really important for technology, especially in our semiconductors, where we have to balance insulation and conductivity. And another way that our elements are grouped is by special groups. And we have our special groups called our alkali metals. We find them in group 1. And they are very highly reactive because they only have one valence electron. The next special group that we have are our halogens. They are group 17, so this group here, and our halogens, they are reactive nonmetals, and they have 7 valence electrons. And they have 7 valence electrons. And the last special group that we have are our noble gases. And we find our noble gases in group 18. Our noble gases are really stable and they are non-reactive because their valence electron shells are full. So their non-reactive nature is due to full valence shells. And categorizing our elements in these groups and these categories is really important to help scientists understand and predict the behavior of our elements and our atoms. So the periodic table has a few different trends. And the first trend that we're going to talk about is the atomic radius. So the atomic radius, that is the distance that we find between the nucleus of our atom and the outermost electron shell and the outermost electron. So the distance between the nucleus and that outermost electron is our atomic radius. And our atomic radius, it's going to increase when we're going down a group and when we're going across a period from right to left. So right here, that element, that is francium. And francium is our largest element. It is the element with the largest atomic radius. And atomic radius, it's going to explain things like reactivity, and it's also going to explain bonding behavior. The next important trend that we have is electronegativity. Electronegativity is so essential to chemistry, and we define electronegativity as the ability of an atom to attract electrons closer to itself in a chemical bond. So electronegative atoms, they have a higher affinity for electrons. And our electronegativity, it increases as we go up a group and across the period. And an atom's electronegativity, it's going to predict bond types. Okay? It predicts bond types and molecular behavior. And the last trend that we're going to talk about is our ionization energy. Ionization energy is the energy that is required to remove an electron from an atom when it is in a gaseous state. And like electronegativity, ionization energy is going to increase as we go up a group and when we go across a period from left to right. And it's important because it's going to indicate how easily an element can form cations. Right? So ionization energy indicates cation formation. And something that I want you guys to understand is that the bigger an element is, so the larger an element is, the greater its atomic radius and the lower its ionization and electronegativity. So, larger atoms, so more atomic radius, is going to cause those atoms to have less electronegativity and ionization energy.